Hello, this is Mr. Huff, and this is a video I want to call Remember That Time I Told You to Do Everything Wrong? We have been looking at data for composites for some time now, so this should look a little familiar to you. So we have been analyzing this kind of data where you've been going through, choosing some data points here and finding ultimate yield strength and that sort of thing. So here, I made a mistake. I presumed that if we selected a data point along this line because it was somewhat linear, that the ratio of force and deflection would be consistent. Based on the idea that the length and the number 48 and the moment of inertia for a given sample are uniform. Okay, and the reason I said that is because that's exactly how it works with a triangle. So this is a graph that shows as you increase, for a right triangle, as you increase the length of the adjacent, the opposite also increases, and the ratio of those two are the same. So you can see here, this is the adjacent length increasing, this is what the length of the opposite side would be, and this is a line that represents the ratio of opposite divided by adjacent, which is the tangent function, right? So that's what I was building that logical assumption on, and actually there's a lot more going on. So let's take a look at some data and kind of talk about what we actually see and what we could also do. So let's take a look at this chunk of data. So what I did is I went through and I picked all the pink 2-inch samples and I got all of that data. You can see there is a lot of data here. So how do you make sense of all of this data if you have just, literally 1,000 rows of data with lots and lots of data in each column? Well, the answer is simply a chart. So here's the chart. Look at what we have here. So this chart is really busy because I've got all of my data sets here, and you can look and see how they all compare. Look at this one down here at the bottom. This is foam by itself. This is another sample of foam by itself. And then these are different samples that include unidirectional and bidirectional. So to kind of cut to the chase for just some essential data analysis and to show you what's going on, I picked the 3 best performing graphs on here. So I picked the highest unidirectional, the highest bidirectional, and the highest piece of foam. And let's take a look at that. So these are the traces of force over time. So these are the force measurements over the seconds for unidirectional, bidirectional, and foam with nothing else. Okay, so that's what we're looking at. So we can see that in one case, the unidirectional was the highest performing sample. And then in another case, here's the highest performing bidirectional sample. And this is the highest performing just piece of foam with no kind of fiberglass reinforcement. So what I had you guys looking at was, pick a point along this line and where it's a linear function and calculate the modulus of elasticity. The problem is this: when you do that, let's take a look at the most compelling one. We'll go take a look at this D. This is unidirectional and the modulus of elasticity. So I've got 2 graphs here. So this is displacement at the bottom. On the left side, we have this blue line, which is the modulus of elasticity. And on this side, we have the force, which is in pounds. Okay. So you can see the force is climbing up. Something happens here. Bam. Right there, we had the highest modulus of elasticity that we saw, and then we saw a step. And then we noticed after this occurs, it starts trailing down and trailing down and trailing down and trailing down. So that tells us that that was probably the yield point. Okay, so at this point, something broke, and then the modulus of elasticity started trailing down. Something terrible happened there. So this would probably be the yield point. But notice if you pick anything along this line, the modulus of elasticity is climbing even faster than that. So that tells us that force over distance is not going to make a flat line. Something more is going on. So what I asked you to do was not useful. What you should have done is, and what I'll have students do next year, is identify the yield point and the ultimate yield strength. And by overlaying the force versus the modulus of elasticity, it's easier to identify where that yield point is. So here is the unidirectional. Then here is the bidirectional. Same thing, this side is modulus of elasticity. So we see that it could be maybe here where we see that shift and it declined and then got better and then gets worse. So it's either at this point or this point, depending on how you analyze this data. Again, if you were to choose something along this line, the force versus displacement is very different as that line goes up, as it trends positive. And then the last one is the one with nothing. This is one with, so you can see that as this line increases, the modulus of elasticity indicates that the yield point is somewhere in here. So that would have been more useful for you to do. So really what I should have asked you to do was estimate the yield point and then identify the ultimate yield strength and use those as your data points. Another way to do a fair comparison would have been to find identical displacement values and then calculate the modulus of elasticity, like at exactly 0.2 inches for all of them or 0.15 inches, something that all of them had. So we needed to find more commonality. What I'm going to do next year is we're going to focus on one kind of sample, and then I'll have one class build a bunch of one type and another class build a bunch of the other type, and we will get lots and lots of data points. And the reason we want to do that is, let's go back and look at all the forces charts. Right here we have these two. These two are just pieces of foam with nothing on them, and you can see that the fail points were radically different based on how high this went before it failed. So what we would need to do is crunch about 15, 20, 30 of these to get a good average, and then do the same thing with unidirectional, and then do the same thing with bidirectional. So and that way we can group a lot of similar data together and get reasonably statistically significant values to use. Okay, and also we could do this analysis where you can identify the yield point based on where the modulus of elasticity downturns or shifts. Okay, so sorry about all that. What I'm going to be looking for on your writing, as long as you support your claims with information, that's fine. I would like to point out though that our highest performing force curve is a unidirectional, and we'll talk more about that in class. All right, thank you. Bye.